Hello everyone, I am going to go over the homework right now from section 10.3. We did this like 2 weeks ago or something. What is section 10.3? It's the section on Eulerian circuits, Eulerian trails, and Hamiltonian paths and Hamiltonian cycles. Okay, let's go. It's a lot of like doing kind of problems here. Let's see if we can do it. I've prepared not much at all for this lecture. Let's go. Immediately, there's a problem like, I don't want to do it. Use the construction from the theorem to produce an Euler circuit for the following graph. That's what Gossett calls them. Okay, so I guess if I'm really going to do this, I think I'm going to start to do it and then give up because I hate this problem. But there's like, I don't know how many edges, like a freaking million edges. And I need to make an Eulerian circuit or Euler circuit, as Gossett calls it. What is that? It's a circuit, so it starts and ends at the same point, at the same vertex. And we're going to use every edge. First of all, can we even do that? Yes, because by a cursory inspection, I see that every edge of this graph has even degree, so therefore it's possible. And it's kind of mindless. I mean, on the one hand, I support making a problem that's so ridiculously big that it's actually kind of hard. But on the other hand, I hate it because I have to do it. This is a good problem to do if this were a programming class where we then can write an algorithm to find one and then just run your algorithm on a big giant graph like this and just see that it works. Anyway, what are we supposed to do? We're supposed to just kind of go, man. So I guess what I'm going to do is just kind of say, this is a simple graph, so I can believe so, yeah. This is a simple graph, therefore I can just list the vertices in order, and that's sort of unambiguous. So anyway, I'm going to go from vertex 10 to vertex 8, and I guess I'm just going to keep going until I get back to 10. And that'll be the first stage. So maybe I want this to be a little bit thicker. Okay, so that's not what I wanted. So this is just going to be a riveting thing that I haven't planned out at all. So here we go, to 11, to 4. And the thing is, man, I can't get stuck. I don't want to go back to 10 because I don't want to go back to 10 yet. So I'll go to 5, and then, I don't know, I'll go to 2. It's possible I should have done this in GeoGebra. To 9. So what have I done so far? 10 to 8 to 7 to 13 to 11 to 4 to 5 to 2 to 9. I guess I can just avoid going back to 10. Maybe I can for as long as possible. So let's see, then back to 8, so that's potentially confusing, but then to 6, and then to 7, 6, and then 7, then to 1, might as well visit 1, hello 1, and then, oh my gosh, then to 8, then to 3, which is the only possibility. So what I say, from 1 to 8 to 3, continuing to 12. Wait, this is actually kind of dumb. To 4. So from 12 to 4 to 6. I guess there's something kind of cool going on here, and then maybe back to 12. From 12 to 4 to 6, back to 12. I mean, what actual learning is happening right now, if anything? I'll tell you what's happening. I'm learning that every vertex has even degree. So since every vertex has even degree, I use up one edge going in and another one coming out. And so I'm never going to get stuck because as I use an edge coming in, I now have an odd number of remaining edges to leave that city from. And so this algorithm, I mean, it is an algorithm, but I'm not following it mindlessly, so that's why I'm kind of cheating a little bit. But I am. Oh, look at what happened. I went to 2 because for some reason I did by accident, and then I'm back to 10. Then I stop. Actually, I don't even have to stop because I think the algorithm I presented in class stopped at 10, but the algorithm in Gossett, when I actually read it later, said, don't necessarily stop when you get to 10, stop when you run out of edges. Yeah. And that must happen at 10 because it can't happen anywhere else that you run out of edges because there are always an even number of edges at any vertex. But since at 10 we started there were an odd number of edges left. And so 10 is one of the places where we might get stuck. But in fact, I'm not really stuck at 10, right? I can sort of keep going. So I read about that later. But anyway, I will kind of maybe switch to a new color here because I did hit 10 the first time. So anyway, so now what? We'll now go to 9 and then go to 3 and then go to 2, then go to 2. So what did I do? I went to 9, 3, 13, 2. Oh yeah, this is just some great video here. 7 and then to 5. Okay, and then to 11 and then to 9 and then back to 5. So 5, 11, 9, back to 5. I'm almost done, by the way. Then to 6, then 3. 6, then 3, then to 11, then to 1, I guess. Sorry, what happened? 3, then 11, then 1. Kind of been neglecting 1. Anyway, here I am at 1. Now what? Well, now I'm going to go to 4, and finally back to 10 again. So what I say from 1 to 4 back to 10. I'm still not stuck at 10, but okay, let's switch colors to blue. Now what am I going to do? I'm going to go from 10 to 1, from 1 to 13, from 13 to 12. And hey, what do you know? Back to 10. Okay, I probably messed up somewhere in my writing, but anyway, you get the big idea. In fact, I kind of faked the algorithm because this time I did not choose my vertices randomly. I tried to avoid going back to 10, and so I didn't have to do any splicing. So maybe this was not only annoying, but I didn't even really get to illustrate the algorithm because of what happened. I sort of just won on the first round. Okay, whatever. Moving on. Here we go, the Peterson graph. Well, if an Euler circuit exists, describe one, otherwise explain why there is no Euler circuit. Well, unfortunately, Peterson graph, there is no Eulerian or Euler circuit. Why? Because of the theorem we proved in class about Eulerian circuits. And the fact is that a graph has an Eulerian circuit if and only if every vertex has even degree. And not only is it false that every vertex has even degree, but in fact every vertex of this graph has odd degree. So there exists an odd degree vertex. Whoa. There exists an odd degree vertex in this graph, and so there is no Eulerian circuit. In fact, every vertex has odd degree. Okay, so that was kind of a dumb problem. Next, 13. For which values of m and n does kmn have an Euler circuit? Provide adequate justification for your answer. And blah, 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 blah. Okay, so we're looking at the bipartite graphs. So I kind of just can tell that what's going to matter is whether they're even or odd. So I haven't actually done this problem, but I did plan to look at a case where one of them is even, one of them is odd, where they're both even, and where they're both odd. So did I prepare these in advance? No. But did I prepare to draw these pictures mentally? Yes. Okay, and what am I doing again? Maybe I want to do this in a light color. So, okay. Once again, riveting video. Well, and 1, 2, 3, 4. 1, 2, 3, 4. Anyone watching at home, I promise you that I have really good handwriting. live on like a whiteboard, but this pen, I do not. Okay, so this, I suppose, is going to be enough to settle this. Okay, question. When do I have an Euler circuit? Well, like I just mentioned, there's an Euler circuit if and only if every vertex has even degree. And, okay, what is the degree of any vertex in a complete bipartite graph? It's the number of vertices in the other partition. So, here the degree is 3 because there is a partition of size 3. Here the degree is 2 because the other partition is 2, because you have relations with every element of the other partition. And, alright, there it is, right? The only way we're going to have a Eulerian circuit is if, I don't think I need to draw these pictures at all. I did kind of waste my time, actually. I should have thought first. Because when am I going to have an Eulerian circuit? Only when the size of my partitions is even. So answer, when n and m are even. And now they want some kind of justification. Well, here's my justification. Because every vertex in KMN has degree m or degree n. And okay, now I've run out of space, so I'll just say the rest out loud. It's only when n and m are even that all the vertices then have even degree. Okay. So 13a, done. For which values of m and n does KMN have an Euler trail but no Euler circuit? Okay, well, I see here that this was actually a little bit dumb. Because this is part A, so there is a there's an Euler circuit for this graph, and now it's not the parity of the sizes of the partitions that matters. It's in fact because here, okay, let's take K35 for a second. Is there going to be an Eulerian circuit? No, of course not, because the vertices all have degree 3 or 5. Is there going to be an Eulerian trail? Also no. Because what is an Eulerian trail? An Eulerian trail is just a trail. So that's one in which we don't reuse edges. And it's Eulerian trail in that every edge is used once. So it's a it's a walk which uses every edge exactly once. But if there's no Eulerian circuit, then it's not possible to start somewhere and use every edge exactly once and end up back where you started. But if there is an Eulerian trail but no Eulerian circuit, then it means it's possible to construct a walk which uses every edge exactly once, but maybe starts and ends at a different place. And okay, we saw from class that will be true precisely when there are exactly 2 vertices of odd degree. Because if you have a vertex of, so that is an example of here, say. So here, this will satisfy part B. Because though there are vertices of odd degree, and therefore there is no Eulerian circuit, there is no Eulerian trail. And basically, what you're going to do is you're going to start at one of the 2 vertices of odd degree, and you're going to end over here. So, okay, here it is, right? You just do sort of whatever. Jom, and then jom, and then jom. Okay, so my answer to part B is when say m is 2 and n is even. It all boils down to the size of the partitions m and n. There is a Eulerian trail, but no Eulerian circuit when there are precisely 2 vertices of odd degree. But for that to happen, then that means that one of the that one of the partitions has size 2, and the other one is not even odd. is what I meant right there. Yeah, so if one of the partitions has size 2 and the other one is of odd size, then there will be exactly 2 vertices of odd degree, and so it will satisfy part B. And if they both have even degree, then there will be an Eulerian circuit. If they both have odd degree, or like K3,4, for example, doesn't work either, because there are 3 vertices of degree 4, but 4 vertices of degree 3, so there's no Eulerian trail or Eulerian circuit. All right, I think we beat that problem to death. 17. Can a simple graph with an Euler circuit have an even number of vertices and an odd number of edges? If possible, provide an example. Otherwise, better prove that it is not possible. I think the answer is it is not possible. Why? Well, okay. So what do I know? I have an Eulerian. What? I have. Whoa. I have an Eulerian circuit. Eulerian circuit. What does that mean? That means, conclusion, every vertex has even degree. Every vertex has even degree. Okay, well, what can I do with this information? Let's apply the handshake. So let's take the sum of the degrees of all the vertices of this graph. Well, the sums of the degrees of all the vertices is going to equal twice the number of edges. But this is just in general for any graph. But the sums of the degrees of all these vertices is going to be sorry, I zoned out for a second. What am I supposed to be doing? I have an even number of vertices and an odd number of edges. Even number of vertices and an odd number of... Okay, I need to think about this a little bit more. Okay, so n is even. The number of vertices is even, but the number of edges is odd, let's say. Okay, so let's just write, suppose that this is true. The organization on this slide is terrible, but I've supposed that I have a graph with an Eulerian circuit, and so every vertex is even degree, and I'm wondering, hey, is it possible for n to be even and the number of edges to be odd? Well, no, because the sums of the degrees of all the vertices then is going to be, how do I even write this? I'm adding up n even numbers. What? Wait, hold on. This is like a little bit embarrassing because this problem's actually like really easy. I'm just like stumbling for a second. The sum of the degrees of all the vertices is twice the number of edges because you're double counting all the edges. Then also, I have an even number of vertices. How do I deal with that fact? Why is that relevant? Because I'm adding up an even number of even numbers. Yeah, so that's it. So the sum of the degrees of the vertices is a sum from I equals 1 to n of the degrees. But what are the degrees? The degrees are all sort of even. Okay. Let's just backtrack a second. The sum of the degrees of all the vertices is 2 epsilon. But now, without getting too bogged down in like notation or whatever, what am I summing from? I'm summing through all of the vertices. There are n of them. But this is a sum of an even number of even numbers. So this is the sum of an even number of even numbers. And if you add up an even number of even numbers, then that is a multiple of 4. Okay, I don't think I need to justify that. That's just like true, right? Add up a bunch of numbers that are even. If you add up an even number of even numbers, then that's a multiple of 4. Okay, but now we have a contradiction because on the other hand, on the one hand, the sum of the degrees of all the vertices is a multiple of 4. On the other hand, let's just say the rest of this out loud. If epsilon is odd, then 2 epsilon is like 2 times an odd number, right? And so that's going to be 4k plus 2. And so this is like congruent to 2 mod for but this is a multiple of 4, and so in fact we get a contradiction. All right, if you listened to all of that, I think it made complete sense. If you look at this slide, it's like terrible, but that's the bottom line. You can't have, if there's an Eulerian circuit, then you have every vertex must have even degree. Well, if you add up all those degrees and you're adding up, supposing that there's an even number of vertices, you're adding up an even number of even numbers, which is the multiple of 4. But if the number of edges is odd, then that is 2 more than a multiple of 4, so that's a contradiction, so it's not possible. All right, that was like one whole homework. It was the homework that we did the day that we proved that a graph is bipartite if and only if there are no odd cycles, and then I recorded it as a video for you to watch later. This proof of me going through the proof that there's an Eulerian circuit if and only if there are no vertices of odd degree. Then there was a homework, which was just those like 3 problems or something, however many we did. Then the following day in class, this was like 2 weeks ago, we talked about Hamiltonian cycles. What are Hamiltonian cycles? In a Hamiltonian cycle, you visit every vertex. Yeah, exactly once. Okay, and specific. That's so. Okay, what is a cycle? A cycle starts at back up. A path is a walk which does not repeat vertices. So a Hamiltonian path is a kind of a path. A path does not repeat vertices. What makes the path Hamiltonian is that you visit every vertex. So a Hamiltonian path is a walk that visits every vertex exactly once. It visits every vertex and only one time. A Hamiltonian cycle is one of those, but also you start and end at the same vertex. So technically, you do visit one vertex twice, but it's the one that you started with. So I don't really consider that 2 visits. Okay. La 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 la. Anyway, there it is. Now we're just gonna like do it, I guess. So here we have a problem. This is the icosahedron, and the question is number 5. Yo, find a Hamiltonian cycle. So yeah, all these very basic polyhedral graph, like the Platonic solids, are all Hamiltonian, I believe. That's what people say. All right, so now it's just a matter of can I do this without embarrassing myself? So what do I need to do? I need to visit every vertex exactly once, and yeah, maybe it is better if I use the highlighter thing. Maybe that's prettier. Yeah, that is prettier. Okay, so good. That only took me half a video to realize that. What do I need to do? I need to visit every vertex exactly once, and I need to end up here at 1. So I think I don't even need to like think about this too much. I think it's like not hard. But if I get stuck, it will be embarrassing because I'm not even really thinking or planning ahead. I'm just gonna go. All right, I take it back. I thought and planned ahead, and indeed it was easy. No. Look at this focus. Ta-da! A Hamiltonian cycle. Woo! That was actually quite fun. Consider H3, otherwise known as a freaking cube. Okay. If an Euler circuit exists, describe one. Otherwise, explain why there is no Euler circuit. Sorry, Gossett, no Euler circuit because there exists a vertex of odd degree. In fact, they all have odd degree. This is a cubic graph. If a Hamiltonian cycle exists, describe one. Otherwise, find a Hamiltonian path. There is certainly a Hamiltonian cycle in the cubic graph. Let's do it. Again, I think I just like barely need to try. But as I say that, what did I start? I started here at 0, 0, 1. So I guess I'll just like, yeah. I mean, this is just like really easy. Ta-da. Just kind of like go along the cube, man. You just visiting every vertex of a cube exactly once. You just kind of like go blah, 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 and you just trace around the cube. So that's pretty easy. So so boom. If a Hamiltonian cycle exists, describe one. I just did, and I also solved this problem that there's none of those. All right, moving on. The Peterson graph. All right. If an Euler... Okay, we already did this one. There's no Euler circuit because there exists a vertex of odd degree. Is there a Hamiltonian cycle? No. This graph is non-Hamiltonian. And I believe this is like... the Peterson graph is sort of famous as this very small graph, which is it's the smallest graph that exhibits a lot of annoying behavior, such as it's a cubic graph, but it's not Hamiltonian. And okay, there's a little bit more to it than that, but that's the gist. So I tried to do this earlier, and then it failed. I looked it up, and it confirmed that there's no Hamiltonian cycle. Is there like some deep reason why? The answer is always yes, but I don't think I have anything to say about that. You can just watch me like try and fail, but I think that's no fun. Because all right, is there a Hamiltonian path? I bet there just is, right? What do I have to do now? Yeah. Then this is just going to be easy. So now all I have to do is visit every vertex once, but without the requirement that I start and end at the same vertex. This is just like a piece of cake. No, what am I talking about? Then I just stop there. All right. Great. It's interesting. My pen interprets any continuous motion as like one mouse thingy. Anyway, there it is. And you can sort of see why you can never get back to A, although how to state that, I would not know. All right, good. Just briskly moving right along. Prove that no Hamilton path, and hence no Hamilton cycle, can exist in the following graph. All right, so what we have here is this kind of symmetrical graph with sort of three pieces. And there's this one vertex 6, which is kind of holding it all together. And, well, what can I say about this vertex 6? It is a cut vertex. It is a vertex which, if that vertex, will disconnect the graph. And so it's kind of like this. What is a Hamilton path? It's a path in which Hamiltonian path. It's a path in which I visit every vertex exactly once. And if I'm going to visit every vertex exactly once, well, then I got to start somewhere, right? Without loss of generality, I could start anywhere inside here, or I guess I could start at 6. Well, if I start at 6, I'm super screwed, because if I start at 6 and I try to go somewhere, say without loss of generality here, well, then I'm never going to get over here or over here, because the only way to get back to those places is to pass through 6. Okay, so I better not start at 6. I better start somewhere inside one of these pieces. Well, it doesn't matter really where you start, because you just do whatever you're going to do, but eventually you got to get out of here, and you're going to get out to 6. And then you're going to go in here, and you're going to do some stuff. But then you're just never going to get back again. So I can't visit vertex. So I guess the idea is something like this, right? If I start somewhere in here, then to get to 6, I need to pass through vertex 8, and then 6, and then to 5. But once I visit 6, I can't visit it again, and so I can never get to 7. So that's a very informal, but I think that was all that was required, argument that there is no Hamiltonian path in this graph. Okay. Make a photocopy of the Tut graph. There are no Hamiltonian cycles. All right. There is, so now they're just telling you, this is the Tut. I just got it in this footnote, describes that the correct pronunciation, I think, is Tut. Okay. So I've been saying that wrong my whole life. What is the Tut graph? Crazy graph, man. Super famous for various reasons. Okay. I think it's like, I forget why it's famous. I think this is one. Let's just look at it. Tut graph. Oh yeah, the Tut graph is famous because it is non-Hamiltonian. Yeah. So in fact, it is famous because it does not have a Hamiltonian cycle. And so it is the smallest, it's actually not the smallest, but it is historically the first discovered polyhedral graph which is non-Hamiltonian. So I think it was believed that there was a conjecture, Tate's conjecture, which said that every 3 regular polyhedron has a Hamiltonian cycle. In other words, every graph, which is the graph of a polyhedron, 3 regular means that every vertex has degree 3. No, is that true? Yeah, I guess that's true. I guess that's what 3 regular means. Then must have a Hamiltonian cycle. This is Tate's conjecture. Every 3 connected planar cubic graph has a Hamiltonian cycle. Yeah, Blah, 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 blah. And sure. Sure. So anyway, getting kind of off track here, but this is why this graph is so famous. And Tut constructed it specifically. This is called the Tut fragment. And the Tut graph is kind of like the union of 3 Tut fragments. And okay, this graph is constructed to be non-Hamiltonian, and it's also constructed since every vertex has at least degree 3 and it is connected, then it is a polyhedral graph. What is a polyhedral graph? Yeah, 3 vertex and planar. Okay, so this graph is planar, connected. Every vertex is connected to every vertex has degree 3 or more, and so this is a polyhedral graph via a theorem that we're not going to prove in this class, and yet it's non-Hamiltonian. So okay. Anyway, later on they found smaller graphs which were also polyhedral but non-Hamiltonian. I want to see this freaking graph. I spent, not gonna lie, an hour 2 weeks ago searching the entire internet for the Tut polyhedra. They're taunting me, man. They're telling me that this is the graph of a polyhedron, but they won't show me the polyhedron. Show me the polyhedron, you cowards. All right. Anyway, back to the class. Let's see. I did this problem in advance so I wouldn't get embarrassed. And I'm going to just do it right now. Let's go. All right, I'll kind of explain my reasoning. The reasoning is something like this. Ooh, this one's a little interesting. Making me think a little bit. Okay, there's this central vertex that I need to... There's this central vertex here that I need to pass through. But, of course, I can only visit that vertex once. And so if I only visit that vertex once, I can use it to get from one section to another section. Let's say from here, let's go kind of like counterclockwise. So I'm going to start up here, and then that means that I'm not going to use this edge on purpose because I want to visit this graph once, and so my plan is to use it the one time is to get from here to here. Therefore, that means I am going to use this edge. So my general strategy is going to be start somewhere up here in this chunk, get along this way, do a bunch of stuff, exit through this vertex, and then go here. And okay, so we begin. How am I going to do this? Well, I guess I'm going to go like, yeah, here we go. Shomp. Let me do this inside. Oh, man. I think I've already like screwed up. Is that possible? No. Oh my gosh. Now I want to go out. And then... Nope, screwed already. Wait, hold on. This is actually this is a little bit harder than I thought. Let me be smart for a second. I know I want to start here, but why? So I'm going to go in, and then I'm going to go... Oh, sure. No. Everything's a little bit different on this picture that I have, but that shouldn't change anything. I think that's what I had before, right? Oh, I see. No, I mean, I really actually don't see. Hold on. What is happening? Let me just focus for a second. Embarrassing video. This happens a lot. Oh, I see. Okay, no, I don't see. This graph I have, this graph that I'm looking at, this graph that I'm cheating off of is work that was done by me, but it's actually confusing me. So it's better if I just think on my own. So let me just think on my own from scratch. What do I want to do? I want to go like this. I don't want to use, no, I can use that vertex, but I want to go like, start here, and I'm going to go boom. No, I'm going to start here, maybe. Yeah, there we go. I'm going to start here. I'm going to start here. No. Oh my gosh. Okay, hold on. So far, so good. I think this is not the only way to do this. Now I'm going to go through this vertex. So if I'm going to do that, I need to be a little bit smart. Or maybe I don't have to be that smart. All right. Here, it should now be easy. At least I hope. Yeah. Okay. So that was not too embarrassing. Boom. I did it. That is a Hamiltonian path. It visits every vertex exactly once. But, okay, great. Woo! Suppose that in a group of 2n people, each person has at least n friends. Okay, so this is a total cheeseball problem because there's basically one thing that to be proved this entire section on Hamiltonian graphs. We talked about in class that whether or not a graph is Hamiltonian, a Hamiltonian cycle exists, is something which lacks a clear characterization. So there's no property that all Hamiltonian graphs have and only Hamiltonian graphs have, but there are some sufficient conditions for a graph to be Hamiltonian, and one of them was that if it's the case that the degree of every vertex is greater than or equal to the half of the number of vertices in the graph, then G is Hamiltonian. Hamiltonian. This was a very long proof. We're going to revisit it in a few minutes. So this is just a very silly application of that theorem. Do you sort of recognize it in the wild? So there's a party, 2n people. The host wishes to seat everyone in a circle such that everyone in the circle is seated next to at least one friend. Is this possible? Well, what is a circle in which everyone is seated next to a friend? In other words, you let your people be vertices. You let there be an edge between them if they're friends. And so putting 2n people together in a circle such that everyone is seated next to a friend is literally just saying, dude, is there a cycle? Because you can just think of every cycle as a circle in which you just go all around. Okay, so they might as well just come right out and say, is the graph of friendships Hamiltonian? And the answer is yes. You're not supposed to give a whole nother proof. You're just supposed to cite the theorem. Yes, because each person has at least n friends. So the degree of every person is, in fact, precisely half the total number of people. Like, so by theorem, yes. That's all I have to say about that. All right. It's just a way, it's kind of the way we already talked about the theorem in the first place, right? If you go, this is a good way of thinking about it. If you go to a party, it's a good way of thinking about the theorem that we proved. If you go to a party and everyone is friends with at least half the people, is what I kept saying over and over again, then a Hamiltonian cycle exists. Well, what is a Hamiltonian cycle? It's a big circle where everyone goes, it's the pants, it's the traveling pants, it's the sisterhood of the traveling pants. You pass around the pair of pants, woo! Okay, are we on the last? This is kind of an easy homework, I guess. We're on the last problem already, which is so hard. But the thing is, we're only going to half do it. Big old theorem. Theorem 10.9, called another sufficient condition for a Hamiltonian cycle. Okay, so this is yet another theorem which... well, it's a sufficient condition for the existence of a Hamiltonian. Have I been saying cycle? Is that a typo? I feel like that's actually just a typo, right? They don't mean Hamiltonian circuit. Wow. Amazing. I thought only I was dumb enough to do something like that. But this is just a typo. That should say cycle. Of course, this is about Hamiltonian cycles. The word Hamiltonian cycle appears like right here. The word Hamiltonian cycle appears right here. So, Gossett, you screwed up. That is a cycle is what you meant to write there. Okay, anyway. The point is, this is just a whole nother theorem that they ask you to prove. All right, if you actually did this entire problem and took it very seriously and went all the way from the beginning, what you effectively just did was to completely redo the proof that we did in class. What was the proof we did in class? Well, I have my gorgeous writing here, so let's just briefly review. There was this theorem, the one that we just took directly from Gossett, from the body of the text. And here's what it said. Well, it's what we were just talking about. If the degree of every vertex is at minimum equal to n over 2, in other words, everyone is friends with at least half the people, then there is a Hamiltonian cycle. And we discussed how disconnected graphs, of course, don't have Hamiltonian cycles because a cycle is a walk that visits every vertex, but if you have two vertices which are in different components, and there is no walk between them by definition, so disconnected graphs are non-Hamiltonian. Complete graphs are Hamiltonian. The more edges you add, the better chance it is that your graph is Hamiltonian. So here, this says that if there are this many edges, then we're good. First, we proved a lemma. The lemma was that this condition, that delta be greater than, that everyone is friends with at least half the people, is enough to ensure that the graph is connected. And we're going to redo this argument in a minute, so I'll leave that alone. So then, restricting ourselves to connected graphs, here's what we said. I want to show that this theorem holds. How do we show that this theorem holds? Well, consider all of the possible graphs that don't satisfy this theorem. In other words, suppose that your graph has n vertices, everyone is friends with at least half the people, but there's no Hamiltonian cycle. And we need to show that such a situation is impossible, so that there are no graphs with these properties. In other words, that this set is empty. Well, supposing that this set is not empty, that there is a graph, with such a properties, well, then there's always like a largest one. We could be more casual than this. We don't have to really construct the set per se, but you just have to convince yourself that there is always a largest possible graph, and largest by the number of edges. And it helps if you want to claim that there's the largest to maybe take for a minute to think about, the set of graphs with this property. And of course, I think I made a big deal in class of talking about how once you give me a graph with precisely n vertices, then there are only a finite number of possible graphs, right? Or once you give me n vertices, there are only a finite number of possible graphs with n vertices, and so this is certainly like a finite set. This set of all graphs with no Hamiltonian cycle, and yet everyone is friends with at least half the people. So therefore, there's the biggest one, and so that's what we did. We said let G be the graph with the most number of edges, and then we say, all right. I know that this graph is connected, and therefore, if we add since it's maximal, it's the maximal graph of this set. If we add even one edge to it, then there'll be no Hamiltonian cycle. And so we added an edge to it. What did we add? How did we add an edge? We added an edge between two vertices that are not already connected. And we know there must be a pair of vertices which are not already connected because the complete graph does have a Hamiltonian cycle. And so since this graph G doesn't have a Hamiltonian cycle, it's not the complete graph, so there must be at least a pair of vertices with no edge between them. And then let's add an edge between those two vertices. And we called that new graph G prime. We called the two vertices which were not adjacent W1 and Wn. We now have this new graph G prime in which W1 and Wn are connected. Well, as this new graph G prime has even more edges than G did, then it certainly satisfies the condition that everyone's friends with at least half the people. But because G was the largest possible graph with no Hamiltonian cycle, then G prime does have a Hamiltonian cycle. And if G prime does have a Hamiltonian cycle, then it must look like this. What is a cycle? It's just a big loop around. And of course, the Hamiltonian cycle must include the W1, Wn edge, because if there was a Hamiltonian cycle in G prime that didn't include the W1, Wn edge, then there would have been a Hamiltonian cycle in G, but there wasn't by assumption. We did this in class. Then I also made an extremely long, detailed write-up of it, and then I also made a video of myself recapping the entire proof. This is like the fourth time. And you would think that this was like the most important theorem or something. I don't think it is. Then there was this like a long conversation in which we reasoned that, look, you can't have a situation where there's like a person, so we define these vertices by the order that they appear in the Hamiltonian cycle in G prime. You can't have a situation where two consecutive members of that cycle are in have the following property, that the first one is friends with Wn and the next one is friends with W1. Because if so, then you could have gone a jump and you would have made a Hamiltonian cycle in G, but we know there is no Hamiltonian cycle in G. So once again, can't be true that W3 is friends with Wn, but W4 is friends with W1. Can't be true that W4 is friends with Wn, W5 is friends with W1, etc., etc. All of those are impossible. And so, via a long sequence of bits of logic, we concluded that these two vertices have the property that the sum of their degrees is less than n. And that is a contradiction, because on our assumption that the degrees of those two vertices are each greater than or equal to n over 2, then the sum of the degrees, in fact, have to be greater than or equal to n. But we just saw that the degrees here are less than n. Okay, why are we reviewing this? We're reviewing this because look again at this theorem. This theorem is saying, hey, prove now a sort of a different, the condition is different. Now we no longer require that every vertex have degree greater than or equal to n over 2. In other words, it's no longer the case that we demand that everyone be friends with at least half the people. Instead, we merely require that for every pair of vertices, the sum of their degrees be greater than or equal to n. But that is actually exactly what we used. In fact, the only time in this entire proof that we used that the degree had to be greater than or equal to n over 2 was to get that the degrees of the sums of the degrees of W1 and Wn is greater than or equal to n. And so what you're supposed to have realized, if you're a very deep and observant thinker, is that this theorem is basically 95% the same as the theorem we proved in class. In fact, this is a stronger theorem because it is a weaker sufficient condition. In other words, it is a consequence of the fact that the degrees, that the sum of the degrees of the vertices are greater than or equal to n over 2 each, that the sum of any two are greater than or equal to n. But in fact, that's all we needed to basically execute this proof. What am I trying to say? I'm trying to say that if merely the sum of the degrees of any two vertices is greater than or equal to n, then that's all I need to basically use this exact same argument I used before. I think the only other part that requires a little bit of care is this proof over here that this graph is still connected. So maybe that's what I'll do. So let me just prove that lemma. It's actually a nice lemma. I almost put this on a quiz. This theorem in its standalone version. Lemma. Suppose so if it's true that the degree of u plus what's their notation? The degree of v. The degree of u plus the degree of v is greater than or equal to n for any u and v in the set of vertices. Then G is connected. Okay, this is a nice little exercise. Let's see if I can just do this without any preparation. I bet I can. So suppose that we have a graph G, or rather, suppose that the degree of U plus the degree of V is greater than or equal to n. Now, so great. And now conclude G connected. And now, I'll do this by contradiction. Okay, so now suppose that G is disconnected. And then this is going to lead to a contradiction. Well, if G is disconnected, then G has at least two components. call those components C1 and C2. All right, maybe I'll do this up here. Let the number of vertices in component 1 be n1, and let the number of vertices in component 2 be n2. Well, what I can say for sure is that n1 plus n2 is less than or equal to n. That is to say, either there are exactly two components and the sum of the vertices in component 1 and the vertices in component 2 equals n, or if there are more than two components, then it will be strictly less than n. Okay, great. Now I just look at how many. How do I do this again? Okay, let me make a picture. So here's component 1, and here is component 2. So the sum of the degrees of any vertices is greater than n. So oh yeah. This is easy, but it's hard, but it's not really hard. I think you just kind of have to push on ahead with confidence. Okay, so what does this mean? Well, take some vertex v1 in component 1, and take some vertex v2 in component 2. Okay, so yeah, that's what I want to do. Okay, let v1 be a vertex in component 1, and v2 be a vertex in component 2. All right, so now I just consider the degree of v1 and v2. What is the degree of v1? Okay, well, look, v1 can only be adjacent to other vertices in component 1. And so, how many vertices are there in component 1? n1 in total. So at most, the v1 is adjacent to every other vertex in component 1. So the degree of v1 has to be strictly less than n1, because even if there are, this is a simple graph, so even if so v1 is not adjacent to itself. So as there are only n1 total vertices in C1, then if v1 is adjacent to every single other vertex in that component, then it will be adjacent to precisely n1 minus 1 vertices. And what is the degree of v2? Similarly, it has to be less than n2, because at most v2 can be adjacent with every other vertex in C2, and there are n2 total vertices in C2. So now if you add up these two inequalities, you get that the degree of v1 plus the degree of v2 is less than n1 plus n2. Okay, but also, by assumption, I'll switch to a new color because I kind of ran out of space. By assumption, I also know that this is true for any pair of vertices. So in particular it's true for v1 and v2. So I also know that the degree of v1 plus the degree of v2 is greater than or equal to n. And have I done this correctly? Sure. So there we go. I get that n1 plus n2 is greater than the degree of v1 plus the degree of v2, which is in turn greater than or equal to n. So this is the I like going into this level of detail. Maybe some people don't need to, but it's this inequality goes here, and then this inequality goes here. And so what do I conclude from this? I conclude from this that n1 plus n2 is greater than or equal to n. But of course it's also true that n1 plus n2 is less than or equal to n. And so, okay, if you want all the rigor, then what we have here is that n is, wait. No, sorry, I did something slightly bad here, which is, in fact, it's strictly greater than, right? Because n1 plus n2 is strictly greater than the degrees, which is greater than or equal to n. So when I apply transitivity with this, when I apply transitivity with the strict inequality and okay, this is too much detail. Then I get that. So okay, so what do I have? I have n1 plus n2 is greater than n, which is in turn greater by this up here, is in turn greater than or equal to n1 plus n2. So that's just a contradiction. I have a thing which is like a greater than itself, so that's just a contradiction. Okay, good. This is kind of a distillation of the same argument. So this is just like a nice little graph theory problem in and of itself. Well, anyway, what does that tell me? That tells me that this condition already implies connectedness. And since this condition applies connectedness, now I just literally repeat the exact same argument from before, right? Take the set of all graphs, which in place of this condition, substitute the new condition. So let S of n be the set of all graphs that satisfy this condition that was that's in the blue box. Let's just call this the blue condition. So let S of n be the set of all the graphs which satisfy the blue condition, have n vertices but no Hamiltonian cycle. Well, take the maximal graph from this set. Add an edge between two vertices that don't already have an edge between them. Now you have a new graph which still satisfies the condition, but has a Hamiltonian cycle. It must pass through, it must use the vertex that you just added. In other words, you just repeat the entire argument. And you repeat all of this, and you conclude with that the sum of the degrees of the vertices is less than n. But that is a contradiction with the blue condition, which is that the sum of the degrees of the vertices is greater than or equal to n. So in fact, it's in some ways almost a simpler proof. I think it's a simpler proof. Because that's just it, right? You get the contradiction. Well, I won't write this slide because it's only this thing in the red. This thing in the red box is what we concluded from this slide, and this thing in the red box directly contradicts the blue condition that I've assumed. Okay, the final thing to do is prove that this is not a necessary condition. Of course, it's not a necessary condition. Come on, man. I can make a very boring graph that has a Hamiltonian cycle. Well, how about this? This is like just the cycle graph C6. It has a Hamiltonian cycle. It's Hamiltonian. But, of course, it does not meet this condition because every vertex has degree 2 in this Hamiltonian cycle. And so the sums of the degrees of any of the vertices will be just 4, and yet n is 6. So this is absolutely not a necessary condition, but it is a sufficient condition. Okay, that completes the 10-3 homework. Goodbye.